Great. And next up will be Cheung, well known to this community as a long-term pioneer in the development of immunotherapies for neuroblastoma, and he's going to talk to us about bispecific antibodies. Thank you, Cheung.
Thank you, the organizers, and welcome. I see a lot of old friends and new faces. And what I'd like to do, though, is John has given you a really nice introduction in terms of target discovery. What I do want to do now is to sort of focus on what we have learned from GD2 and how we can take that further. So this is sort of my cartoon and understanding how immunotherapy, at least in the past 30 years, has worked. And you can see that in the schema of things, you actually need two to tango at least. You need the antibody and you need cells. And now we appreciate that understanding antibody is only part of the story. Understanding the cell could be extremely important. For example, we now know that the NK cells have checkpoints, and 3DL1 was one of those checkpoints that actually inhibit its function. And then the other thing is also we now know that the Fc receptor polymorphism and complement receptors CR3 is also important in the myeloid-mediated ADCC. And even for the macrophages, we were one of those people who were crazy enough in the early days to actually use MCSF to treat patients with cancer. Of course, I saw the patient's tumor were growing a little bit faster. This was never published, but that's the thing is that you have so many data that's unpublished, and I think that what we like to know is to let's learn from what we know so far. Now, the idea that maybe that the T cells may not be, or the classic T cells doesn't work as well because of low MHC and maybe the peptides are not expressed, that's obviously a problem, and that's what we go into CAR T cells, and bispecific is really what we've been focusing on. Now, just to quickly run through what we've learned from the GD2, that we can now use GD2 antibody 3 of 8 in combination with a cytokine, GM-CSF, to get 87% of patients who are primary refractory into bone marrow remission. So this is a very high, response rate. And in fact, if you look at the long-term outcome, after about 14 years of follow-up, the patients treated in primary refractory, at least 45% of them are alive and well. And those patients treated in second remission, you can see that these are also doing well. And that's why we actually got to the first remission patients, and the outcome was also very favorable. However, one thing that we learned was that soft tissues do not respond as well as we want. And now we understand that NK cells actually don't travel to every place we want. And at least those cells that are CD16 positive only travel to some places, such as bone marrow. And this is why we have such a great response in the bone marrow, but not so much response in soft tissues. And the other thing is also is the brain is the ultimate. Antibodies cannot get to the brain, and this is why we have actually brain metastasis. And there are other things that we've learned. And the main thing, though, is that we have never seen a long-term toxicity, despite the fact that ganglioside GD2 is on neuronal cells. And that's very comforting. After 25 years of follow-up, we have no long-term toxicity. And this is where we got us to the vaccine trial, because GD2 is such a great system. So we have a vaccine trial ongoing now that's now followed up to 8 years. And the data is very encouraging. The patients who are in second remission, and this we talked about this morning, can relapse patients be cured? I think this is at least an inkling that may be potential for curing patients even after they relapse. And this is another study that's ongoing, which is very interesting. Now, we learned even early on that not all targets are the same, and not all modalities work the way you want it. For example, when we look at some of these imaging studies, these antibody 3 of 8 goes to tumor beautifully. It goes to tumor and not to any other organ. And you thought, well, this is it. This is the magic bullet. Let's target radioisotope. But it turns out, when we start to study early on using antibody 3 of 8, in substituting for transplant, and then we tried another study, which is N7, will be combined with radiolabeled antibody. Initially, we were encouraged. Looks like the patients are doing better, but in the long term, there was no real benefit adding in the radiolabeled antibody or as a drug conjugate in a way. So this is an important lesson that we learned. And one of the things that we noticed was the therapeutic index, which is the area under the curve in the tumor versus area under the curve in the blood, is only 4:1. And you might say, well, this is because of 3 of 8. No, it's because of all IgGs. All IgG has the same problem, and you'll see that in a second. So the CNS was a big problem for us, and this is where we went on to study another approach, and this is using an antibody against B7H3 tagged with a radioisotope injected directly into the CSF. And these are patients who have brain metastasis, and what it is that when you look at the imaging studies, you can see the radiolabeled antibody tracking the CSF, and are localizing some of the tumors in the leptomeningeal space. One thing that is striking was the dosimetry tells us that the dose to the tumor now, instead of 4:1, is 50:1. And this is where we begin to see a benefit of these kinds of approach. And in fact, this is the outcome of all these patients now who had brain metastases, a study led by Dr. Kramer, now up to 13 years for follow-up. These patients are all in school or doing really well. And so these are patients that we thought that are not curable in the past, and now using them, treating them with an antibody against B7H3, radiolabel injected to the CSF, they are now in remission 55% or more. This is in contrast to what we were seeing before the era of the antibody, when nobody survived. So this is another example where dosimetry tells us that therapeutic index is absolutely important. And with that, we actually went into the DIPG, because if you can inject in a compartment antibodies directly, why not put it into the pontine glioma? And this is a study that's been ongoing, led by Dr. Swedane and Dr. Kramer. And what it showed us was that the dosimetry, again, was very interesting. As you can see here, this is the first level that we are looking at, and this is published or going to be published in Non-Cell Oncology. But when you look at a slightly different formulation, that was something we want to do now, you can actually deliver a dose up to 60,000 rats to the brain tumor with minimal radiation to the rest of the brain. Now, this is the beginning of, I think, a therapeutic era, because that kind of dose can melt things. In fact, I was saying, if you go to 100,000 rats, you can treat vegetables and kill all the viruses and bacteria. So this is the kind of dose that was not possible in the past. And now we are. And with that, you can see that the dose to the rest of the brain is still less than 500, which is very tolerable. At least they're not entirely harmless, but it's tolerable. So this approach was now applied to the intraperitoneum, where you take the radiolabeled antibody and inject it into the peritoneal cavity. And this is the diseased desmoplastic spiral cell tumor, which has always been difficult to cure. And with this approach, we can now see that we have a much better survival than previously when we were using base chemotherapy, abdominal radiation, and surgery. So this concept now, again, trying to improve from what we have in the past using PK, very important, dosimetry is where led us now to the new era. How do you empower these antibodies? We can use, for example, humanizing. Humanizing antibodies make it less immunogenic, for sure. You can make antibodies that have a different glycoform, let's say. Besides taking out the fucose, we can also change the mannose, and this is something we published already. By doing that, you increase the affinity of these antibodies for the Fc receptor, and therefore they kill tumor cells much better. So this is another approach. But I'm going to focus on today on the T cells and the radioisotope. And I call them cage isotopes because this is where it has failed in the past, when it's not cage. So how do we do that? Well, we actually go into protein engineering as a new way to develop drugs. And what is shown here is that you can take a regular IgG. As I said, you can change the glycoform and make it a high affinity to Fc receptor and maybe increase the NK cell killing. Or you can make bispecific antibodies, and this is where we are focusing our effort on. By putting a single chain, these are all humanized systems, by putting a single chain to the light chain, you can now make it a bispecific antibody, this end binding to the tumor and this end binding to T cells. By the same platform, we can attach another or different antibody, and this is an anti-DOTA antibody. So DOTA is the cage, and just remember, I'll come back to that. It's a cage where we can essentially enclose metals. And what we use for MRI scans, the contrast agent is DOTA, cage gadolinium. So DOTA has been used in humans for many, many years. It's a very safe ligand, but has some beautiful PKs in it. So with this, we explore then the options. Now we went to the different kinds of bispecifics, and I think the field is actually kind of expanding right now. And we focus on a platform, what we call 2+2, which is bivalent to the tumor and bivalent, quote unquote, to the T cell. The reason for bivalency is you can imagine if you're trying to do a monkey bar versus 2, it's much better. You can hang onto the tumor much more tighter, and in fact, it translates into much better efficacy. Now, this is in contrast to some of these other platforms, which the BiTE, for example, a license for CD19, and also heterodimer, which is now the new license bispecific by Cheung, which is for factor VIII for hemophiliac. Only 2 platforms so far that's been licensed. But what we are doing right now is to try to use a slightly different approach. And what this is an idea where you can actually engage targets using 2 arms, but engaging the T cells, not exactly 2 arms. It's almost 2 arms, but it's not quite. And this is the magic. So let me show you what it does. So if you take a tumor that is cold, and typically for neuroblastoma and for many adult tumors are cold. There are no T cells in there, there are no lymphocytes in there. And what you do is if you take these cold tumors, you put them into, let's say, a skid mice, and then you tag your T cells with luciferase. And you can see those T cells that are tagged with a luciferin, and they, if you inject it IV, will go to the lung as expected. And the tumor was completely cold. And if you inject it into the peritoneum, it stays in that peritoneum, and the T cells don't track, and the tumor is cold. But as soon as you inject a bispecific antibody, and this one, for example, against GD2, you can see that T cells track into the tumor immediately. Now, the magic of that is that when you go into tumor, the T cells start doing things. And you can see here that, for example, a tumor that is cold with the bispecific antibody now becomes hot. And with all the cells that are going in there, there are a lot of things that's happening. We can show that the tumor now with TIL cells, they also looking for the PD-1, PD-L1. You can see that as soon as the T cells get into the tumor upregulate PD-L1, which is not surprising. Like every other tumor, it does exactly that. But despite that, when you treat these mice bearing tumors with the bispecific antibody in the presence of T cells, the tumors all go away. And this is in contrast to all the other controls where you have either a monospecific or bispecific against other antigens or other T cell markers. You don't have any kind of tumor control. So this is an interesting concept. And we've now shown that these T cells drove into tumors. They can shrink tumors in skid mice. They can shrink tumors in transgenic mice. And we've done it with cell lines. We've done it in PDXs. So the concept here is that these bispecific antibodies can now take T cells, the classic T cells, polyclonal T cells, in fact, every T cell, if you think about it, into a tumor and do the job for you. One thing that was really striking, though, was when we start looking at this question, when you give an antibody like bispecific into the blood, what does it do? Does it go to the tumor first or the T cell first? And this is a sort of a conundrum we have. We know what exactly how you design these antibodies. So we started off looking at, well, maybe just look at how it goes to T cell first. But if that's the case, why don't just arm T cells? So this is what we did. And T cells, for example, you can culture them in vitro. And then after you culture them for a while, you mix them with the bispecific antibody, 20 minutes at room temperature, and inject it into an animal model. And what is shown you here is that if you do that, a tumor that's growing, when you get those arm T cells and tiny amount of antibodies, microgram per million, for example, these tumors all go away. This is a PDX model compared to other control bispecifics. So again, it says that these arm T cells are very potent, and the way you arm them is actually very simple. Almost as good, you might say, as the idea of maybe genetically arming T cells. And one thing that we actually saw that was not a little bit surprising to us is when we compare the different platforms. We have the BiTE, we have the heterodimer, we have our 2+2. The only one that actually worked well was the platform that we adopted. The BiTE platform did not seem to work as well or work at all And heterodimer also didn't work as well. So one of the things that we realize now is that there seems to be a certain kind of platform, antibody platform, that help this arming approach that can actually engage this T cell so that it will go to the tumor and shrink tumors for you. In fact, the idea is maybe you can use allogeneic T cells that are already primed to, let's say, infectious agents like EBV, CMV, and then use them as a way to target T cells. I wanted to bring your attention to one of the phase 1 studies that's actually still ongoing that was done using a slightly different bispecific. That's a chemically conjugated bispecific, but it's using the same humanized IgG8, but using a mouse OKT3. So we've applied that approach, the bispecific approach, to a number of human targets. And the first obvious one was HER2, because HER2 is such a well-studied molecule, and the antibody's been around for many, many years, and many millions of patients have been treated with this Herceptin antibody. So with the HER2, what we showed was when you make that kind of bispecific, besides having an anti-proliferative effect like Herceptin, it now can utilize T cells to kill tumors. So we can show that they can kill tumors in cell line tumors or PDXs. And not just for breast cancer, actually for gastric cancer, which is a much lower expression than most breast cancers. And again, we showed that this platform was relatively insensitive to PD-1 and PD-L1 inhibition, although you can enhance the effect of these antibodies by combining with anti-PD-L1. And shown here is an example. Tumors will go away with the bispecific. And then again, when you show the immunohistochemistry, these T cells, as soon as they track into the tumor, they upregulate, they stimulate PD-L1 expression in the tumor. But despite all that, the tumor is still going away. So the bispecific now has been applied to a number of targets, and not every one of those work. And again, I say that not all targets are identical. Some work in certain ways and some don't. But moving on to the next subject, and that is the isotope. And what it is we now know that Madame Curie was a brilliant physicist, brilliant chemist, and she understood the potential radioisotope. She let the beast out that killed her because she never tamed it. So how are we going to tame this beast, radioisotope? And we tried, many people have tried. And one of the things that we know now is that there are certain isotopes that do certain things. For example, they travel certain distances, like alpha emitters. They're very powerful, but they travel short distances. They're much more precise compared to beta emitters, like lutetium. But one of the interesting observation all along has been that IgG, as I mentioned earlier on, the 4-to-1 therapeutic index is classic for IgG, whether you're looking at drug conjugates or radioisotope. When you tag something to an IgG, it circulates and it will bind to the tumor, and the uptake in the tumor is in brown. What is in the blood is in green. So the area under the curve, which is a measure of exposure, drug exposure, is not very favorable, as you can see from this area under the curve. It's the best 4-to-1. And this is your problem. When you have something that every time you hit the tumor 4 times, it hits you once, that's not very good therapeutic index. So this is where we start looking at the bispecific antibody approach to take a multi-step. And the multi-step is shown here, that if you take an antibody and attack it with a anti-DOTA single chain, you send the antibody first into the tumor without any isotope. And what this will do is saturate the tumor, and at some point, you can either clear whatever's in the blood or let's wait. And then, after it's all clear from the blood, now inject the radioisotope, which is the DOTA, what I call is the cage. Here's the cage that carries the isotope. And the isotope goes in to the tumor, and when it doesn't bind anything, it clears out. There's nothing better than have a drug that goes into your body, does its job, and get out. I don't want anything to be sitting in me if it's not doing anything, whether it's a protein or DOTA or whatnot. So this concept of a PK-based approach is really important. Now, the reason why this is also fascinating is because it's a plug-and-play system. You can take any antibody and hook anything to the light chain, or hook the DOTA to the light chain and make it to bispecific and do the multi-step targeting. And also for the DOTA part, you can actually conjugate or you can use lutetium, but you can also use other isotope, which is also very important, not just lutetium. There are many isotopes that can be caged in a DOTA or DOTA-like chelator. So this is to show you an example. For neuroblastoma, for example, for GD2, you can deliver about millicurie into the mice and show that you can shrink tumors, completely eliminate tumors. But that's not all there is. Everybody can cure a mouse. When you dissect the mice, there was no radiation damage in the mouse. None. Zero. So the mouse has never seen radioisotope, essentially. And this is the beauty, because you can now begin to appreciate that the kind of the area under the curve ratio is 142 to 1. You're not talking about 41, it's 142 to 1, so you can deliver radioisotope to eliminate tumor cells without actually damaging the body. So you may say, well, let's take a step further. Give me another tumor, more radio-resistant, not neuroblastoma, just radiosensitive. Well, take colon cancer. This is an example of colon cancer. We get 5 times as much millicurie, and you show that the tumors would all go away also. And the ratio, not 142 to 1, it's 93 to 1. But when you dissect the mice, again, there was no evidence of radiation damage. So here's like pushing it now to the ceiling almost. Even then, you don't see radiation damage. And this is, again, example where the PK, you can take advantage of it, could be so amazing. And this is to show you, besides being a therapeutic, it is also an imaging agent. It's what we call a theranostic. So you can actually image the tumor using by SPECT, or you can image the tumor by PET, because Yttrium-86 is a PET imager. And again, it can be chelated or caged in the same DOTA molecule. Let's take a step further. I talk about actinium, which is an alpha emitter, which is one of the most difficult so far in getting it to work in humans. Alpha emitter conjugated antibodies in the past have failed because it stays in you. And when it stays in your body, it damages your body. So the idea of caging actinium is an interesting concept. And again, what it is now it's in the cage. It's going to go into the body using, again, the whole concept of pre-targeting, go into the tumor, and if it's not going to the tumor, out in the urine within minutes. That's where you can get that kind of selectivity that we want to see. And again, to show you, this is just an alpha chelator using the same kind of DOTA handle, and you can show that the biodistribution was actually very favorable. And in fact, you can use a surrogate, which is indium-111, to do dosimetry to find out exactly where the stuff is going. So we're now taking a step further, and that is that you talk about this antibody that you have to use maybe a clearing agent. Why not use protein engineering to make it make a better drug? And this is what we did. What we did was the idea of using a standard tandem single chain construct, which is the BITE, except that in this construct, one end is binding to the tumor and the other end is binding to DOTA. So we tetramerize. We now will put a little tag into the protein and make it into a tetramer. So with the tetramer, 4-arm binding to the tumor, 4-arm binding to DOTA, we send it into the tumor, and what it does here is that it will clear the body within 24 hours without even clearing agent. Why is that? Because the tetramer breaks down into monomer. So the beauty of this tag is that it will go in as a tetramer, it will break down into a monomer and get out of the body. And by 24 hours, you can now inject your DOTA and you achieve exactly the same results as you achieve with the 3-step method. And the beauty of that also is that we have a plug-and-play system where you can take any antibody you want. You can take GCP2, for example, or L1CAM, and try to do exactly the same thing. And just to show you that this is for real, because when we take mice with tumors and you treat them with this kinds of approach, multi-step, you can see the tumors will grow away rapidly, as you can see here, while the uptake in the tumor persists because it's a tetravalent molecule, not just even bivalent. It's a tetravalent molecule, so it binds extremely with high avidity. And then the blood clearance is very fast. And the ratio of tumor to blood is very favorable with this 2-step method compared to the 3-step method. So sort of went through a lot of things on platforms. We look at adjuvants, we look at humanization, FC enhancement, T-cell bispecific and DOTA bispecific. All of this really is trying to get us to a better drug, a more specific drug, a more effective drug against any tumor, neuroblastoma and whatnot. Obviously, we still focus on some of these targets and some of these old targets, which I think should not be forgotten because they are really nice, good targets for potential immunotherapy. And what we're doing now is actually look at the whole spectrum of known targets that we know have been tested in humans, has been tested safe in humans, but can be applied to both the T-cell bispecific as well as to the radioisotope, cage isotope approach. And this would cover essentially a lot of the pediatric tumors we see today besides neuroblastoma. Anyway, so sort of try to summarize for you what we've been doing over this maybe last 5 or 10 years, but I do think that protein engineering, and after you find the target in the IgG, can really expand the possibilities in terms of how you're going to treat pediatric tumor and maybe cancer in general. Thank you.
Thank you. Maybe time for one question?
So Dr. Alice Yu is going to ask a question.
I'm just concerned about the weak expression of GD2 in normal brain tissue, the neuronal cells. Do you see any toxicity in your direct conjugate, including your ribo conjugate?
Yeah, please repeat.
So the question was, GD2, as we all know, is expressed in neurons. And we've been using mouse model all these years. Now in the mice, the GD2 expression is much lower. So the mice actually probably wouldn't be able to tell you what the toxicity is. Back in the days when Dr. Kramer was doing intra-Ommaya, she was injecting intra-Ommaya anti-GD2 antibody into the primate. It's interesting that, and now Kim can correct me, we didn't see any neurotoxicity, at least no acute neurotoxicity. There's some fever, there's some meningismus, but there's really no neurotoxicity. Again, in our patients now followed for 25 years, I think our now first patients are going to medical school. So you can see that they are really very, very smart kids. So I don't think there's any reason to doubt that damages the neuron.